In the basic theory of transmission line, we have actually obtained the expression for the voltage and the current as a function of distance. When you measure the distance with respect to the sending end or the generator end, then how the voltage and current varies with that distance, the results we have obtained in our previous lecture. And you have seen that at a distance x from the sending end, the voltage V of x is given by this expression, Vs times cos hyperbolic gamma times x and plus Z0 times Is sin hyperbolic gamma times x. And in the similar manner, we have also obtained the expression for the current I of x, which is given as Is times cos hyperbolic gamma times x plus Vs over Z0 sin hyperbolic gamma times x. I hope as we have learnt about these two equations in our previous lectures, so definitely you are aware of each and every quantities used in this equation. You know, this Vs is what? This is the voltage across the sending end. And this Z0, you know, this is characteristic impedance, and Is is current at the sending end. The most important quantity in this equation is actually this gamma. And you know, this gamma is called propagation constant. Why it is called propagation constant and what is its importance in the discussion of the wave propagation through this transmission line, we will see in this lecture. So basically in this lecture we are going to discuss this propagation constant gamma. Okay? As we have seen earlier, that the propagation constant gamma is given as a square root of the product of impedance and the admittance of the circuit. And you know, this Z is impedance, Y is admittance, and Z is equal to R plus J omega L, and Y is equal to G plus J omega C. Okay? Here you know, this G is the conductance, okay, and R is resistance, L is inductance, C is capacitance, you know, and J stands for the imaginary, that is J equal to a square root of minus 1. Okay? In fact, this quantity gamma governs the manner by which the voltage and the current varies with x in this transmission line. In which manner this V and I will vary with the variation of x, that is actually determined or that is governed by this quantity gamma. Okay? So you can say that this gamma actually governs the way in which the waves are propagated, and therefore it is called propagation constant, because the propagation of wave through this transmission line is governed by this quantity gamma. Okay. Now we are going to define this propagation constant for unit length of the transmission line. In fact, for unit length of transmission line, this propagation constant gamma is defined as the natural log of the ratio of the current at the sending end and current at the load end. Okay? So I have mentioned here, you can see the propagation constant of a line per unit length. Mark it. This is propagation constant per unit length. This is defined as the natural log of the ratio of the steady state currents entering and leaving the structure. You know, the current which enters in this transmission line, that is actually denoted by the symbol Is. This is current at the sending end or at the generator end. and the current which leaves this transmission line at the, that is the current at the load end, which is denoted by the symbol IL. So mathematically, this propagation constant per unit length of the line is defined as logarithm of Is over IL to the base e. That is the natural logarithmic value of Is over IL. So in this way, we define the propagation constant of a line per unit length. Okay. But you have seen in the previous lecture that actually this propagation constant is in general a complex quantity. And if it is a complex quantity, definitely it will have a real part and an imaginary part. So in general, this gamma is expressed as alpha plus j beta, where this alpha, this is called attenuation constant and beta is called phase constant. In fact, how the wave gets attenuated, how its amplitude decreases with increase in distance x, that is determined by this quantity alpha, and so it is called attenuation constant. Okay. Now let us see this equation 3. You can see this is gamma equal to log Is over IL. Okay. So Is over IL, this will be simply equal to e to the power gamma. But you can see gamma is equal to alpha plus j beta. So this will be e to the power alpha plus j beta, and this can be written as e to the power alpha times e to the power j beta. Okay. This is the value of the ratio Is over IL. Okay, Is over IL. Now, in fact, if you consider that this I1 is the current entering the line and I2 is the current that appears when the current traverses a unit length along this line. Okay. And this I3 is the current appearing again after the traversal of unit length in this way. In fact, if you say that I1 is the current entering the line, the current I2 at a unit distance further along the line would be attenuated in magnitude by an amount alpha. If alpha is the attenuation constant, then this I1 is get attenuated and it becomes I2. Okay, it means you can say that the value of the current will decrease by a factor alpha. Okay, after each unit distance, and at the same time, actually the phase of the current get retarded by the amount beta radian per unit length. Okay. In fact, if you treat the current as a vector, that is as a phasor, then the locus of the current arrow will be a long spiral, as I have shown in this figure, you can see. And in the absence of attenuation, that is when alpha is 0, this figure becomes actually a circle. So in this figure I have shown the locus of current phasor, or you can say current vector. Okay. Now, in fact, this attenuation constant alpha does not depend on the frequency, but the phase constant beta varies linearly with frequency. Okay. In fact, it is also, you can see that this Z0, which is called the characteristic impedance, that is also not a function of frequency. Okay, it is also independent of frequency. And the attenuation constant alpha in terms of this characteristic impedance is given by this expression. You should remember it. Alpha equal to 1 over 2 times R over modulus of Z naught plus G times mod of Z naught. Okay. So this is the expression for alpha in terms of Z naught. Now, if you consider that there is a situation when this G is very small, or you can say that the conductance is negligibly small. If it is negligibly small, then this second term may be neglected in this expression, and then alpha will be simply equal to 1 over 2 times R over mod of Z naught. Okay? So in this condition, the value of this attenuation constant depends on the resistance and the modulus of the characteristic impedance. Okay? In fact, the distortion in the current or distortion in the voltage, when you say distortion, that means there will be some alteration in its value, its shape, its manner of variation, that is called distortion. So what will be actually the condition for low distortion? Now we are going to see. You know, Z naught, which is the characteristic impedance, its modulus is equal to a square root of L by C. I think you have an idea of alternating current, and if you have studied alternating current, you can see this Z mod of Z naught is given by a square root of L by C. So in general, when you will take the expression for this modulus of Z naught, which is a square root of L by C, and find the value of alpha, which is attenuation constant, then let us see what will be the result. Instead of this modulus of Z naught in this equation 6, now we will write a square root of L over C. And then you will get that alpha is equal to 1 over 2 times R times a square root of C by L, because here Z naught is in denominator, times G times a square root of L by C. Okay? Now you can see from this result that this alpha depends on all the 4 line parameters or all the 4 line constant. That is, it depends on R, L, C and G. And if there is no distortion, then this attenuation constant will be 0. Or you can say, if ideally you say that this attenuation constant alpha is 0, then there will be no distortion. It means if the sending end sends a sinusoidal signal over the load, same sinusoidal signal will appear. But if there is distortion, then if you will apply a sinusoidal signal, then over the load, the sinusoidal signal will not appear, but it will get some distortion. Okay. So ideally, if we take there is no distortion, then this alpha, that is the attenuation constant, will be 0. And if attenuation constant is 0, then you can see from this equation 8 that in this condition, R times root over C by L must be equal to minus G times root over L by C. Okay? But as you know that the quantities used in this quantities in LHS and RHS are never negative. So actually it means the magnitude of this quantity R times root over C by L and G times root over L by C should be equal. And therefore, when you will actually make here a cross multiplication, you can see that this will be equal to RC equal to GL. So in magnitude, if you will take RC equal to GL, then for that value of attenuation constant alpha, the distortion will be minimum, or you can say distortion will be very low. So in case of low distortion, what will be the attenuation constant? For this, we will use this relation RC equal to GL, or you can say that this C by C by L. From here you can see C over L will be equal to G, C over L equal to G over R. So instead of this root over C over L, you can write G over R, and instead of L by C, you can write R by G. Okay. So making this substitution, the value of alpha will be 1 over 2 times R times root over G by R plus G times root over R by G. Here you can see this first term will become Rg, root over Rg. The second term will be also root over Rg. So inside this square bracket there will be 2 times of root Rg. That 2 and the 2 in denominator will cancel out, and therefore alpha is simply equal to a square root of Rg. Okay, and from here you can put the value of G. This will be equal, if you will find the value of G, this will be Rc over L. Rc over L. So this root, when you will put that value of G, your result will be R times root over C by L. So this is the value of alpha for which there will be low distortion. Okay. So if your aim is to lower the value of distortion, what you should do? See this expression. For low distortion, the attenuation constant alpha should be small, and alpha will be small when resistance R and the capacitance C are small. But on the other hand, this inductance L is large. So the condition for a smaller value of alpha, that is for low distortion, is what? For this we must have larger resistance, larger capacitance, but a smaller inductance. Okay. So I have mentioned, you can see, hence to have low distortion, we should decrease the value of R and C and increase the value of L, because our aim is to decrease the value of alpha. For this, R and C should be small and L should be large. In fact, the increasing the value of L in this case is known as loading of transmission line. When you say that we are going to load the transmission line, it means you are saying that we are going to increase the value of inductance. So what is the condition for a small distortion or low distortion? The condition is resistance R and the capacitance C should be small and the inductance L should be large. Actually, in that condition, this attenuation constant alpha will be small, and which results in the low distortion. Okay. So I think now your concept regarding this propagation constant and this attenuation constant, the phase factor or phase constant, is clear to you. Okay. Thank you very much.